Welcome to the Walton Pi. Today we're going to be talking about related rates. So the idea of related rates is that fairly often we come across situations where there is more than one thing that can change at the same time, but some things are much easier to measure than others. The idea of related rates is that if we can measure the rate that one part of the problem changes, we can use that to calculate the rate the other part of the problem will be changing at the same time without having to directly measure it. Our goal in setting these up is to try and find a formula or expression that's going to relate the two quantities we want to compare, and then take the derivative of the entire expression to then try and solve for one rate in terms of the other. For example, if we were to measure the area of a square and our formula was a equals L squared, where L is the length of the side of the square, we can measure how we are changing the side length pretty easily, but then the area might not be quite as easy to do. So if we were to take the derivative of everything with respect to t, we would get the derivative of a with respect to t is equal to 2 times the length times the derivative of the length with respect to t. So that means if we know the side length and we know the rate the side length changes, we can immediately calculate what's the rate that the area of the square is changing. Let's go through a couple more examples together. So let's suppose that you've built a bubble gum blowing robot that can blow out at a constant rate. So you can know the rate that the air is blowing into the bubble. That's really easy to measure. You can just have a little gauge inside the mouth of the robot that's measuring how fast air is going through, so we can measure the rate the volume changes very easily. But it would be hard to measure the rate the radius changes without accidentally popping the bubble. Since we don't want to do that, we would be able to measure the rate the volume changes, but not the rate the radius changes. So let's go through and figure out how we would be able to set up a related rates problem. So let's suppose that our bubblegum robot is blowing 10 milliliters of air into the bubble every second. That tells us that the rate the volume changes is equal to 10, and it's positive because it's increasing in volume. We now have a formula that relates volume to radius. So we know volume, we want to know radius, so we have to find a relationship between them. So volume equals 4/3 pi r cubed. And so what that means is we are going to be able to figure out what's the volume. So we have our volume, we now need to figure out how can we get a dr dt, so the rate the radius changes. We are going to do that by taking implicit differentiation and taking the derivative of everything with respect to t. So that's going to give us dv dt is equal to 4 times pi times r squared times dr dt. So what that means is we now have a relationship between dv dt, which we know, and dr dt, which we don't. So if we solve for dr dt, we are going to be able to get that dr dt is dv dt divided by 4 pi r squared. Or in other words, since we know dv dt is 10, dr dt is 10 divided by 4 pi r squared. So if we know what the radius is, we can immediately find the rate that the radius is increasing at that time. Let's do another example together. Let's suppose that you left a 13-foot ladder leaning against the wall of your house with the base 3 feet from the wall. I know this is very unlucky. It's 13-foot ladder. It's propped up so you can walk under it. This is not going to end well. And so as you're playing fetch with your dog Fido, he bumped the ladder and is going to start sliding away from the house 1 foot every second. I told you this wouldn't end well. It's 13-foot ladder. Ladders and good luck, they don't go together. So let's start by drawing a picture so we can try and get a good relationship set up if we are trying to figure out how fast the ladder is sliding down the wall. So here's our little diagram. It's a 13-foot ladder. Let's let x measure how far the base is from the wall, and y is how high up the wall it is. So if we know that it is sliding 1 foot per second away from the wall, that means that we know that dx dt is equal to 1. To figure out how fast it's sliding down the wall, we're going to need to figure out what dy dt is. So a relationship that can relate these is using the Pythagorean theorem. We know that x squared plus y squared is equal to 13. So if we want to then use that to help us solve the problem, we're going to take the derivative with respect to t. So derivative of x squared is 2x dx dt, the derivative of y squared is 2y dy dt, and the derivative of 13 is 0, since 13 is a constant. So that gives us that 2x times dx dt plus 2y times dy dt is equal to 0. We can now solve for dy dt. If we solve for it, we end up getting that dy dt is x over y dx dt. We can then solve for x and y at a time t, and we know precisely how fast the top of the ladder is sliding down the wall. The reason that this negative sign is important is the negative says it is heading in the negative direction, meaning it is heading down towards the origin, which makes sense. If the bottom of the ladder is sliding away, in order to keep the length of the ladder the same, the top will have to be coming down. And so that's how we would be able to figure out how fast the ladder is sliding down the wall. So for example, if x was 5, then y would be 12, and so then we would be able to find that at that time dy dt would be negative 5/12. It's going down 5 inches every second. So that is exactly what we are doing here. How fast is the ladder sliding down the wall 2 seconds after Fido bumped the ladder? We know that at time t equals 0, the ladder was at 3 feet from the wall. So now 2 seconds later it's 5 feet from the wall, so y is 12, and so that means that dy dt is minus 5/12 feet per second, which 5/12 of a foot, that is 5 inches. So it is sliding down at 5 inches every second. I hope this video was helpful in understanding related rates. Please check out some of my other videos, as watching them is directly related to being able to do better on any of your calculus tests. I hope you all have a great rest of your day. Please like and subscribe if you haven't already so that I can continue to make these videos, and good luck with the rest of your math.